Welcome to calculus. You will master complex problems, but forget how to add. On this episode, Stevenson will demonstrate
we can use a definite integral over a closed interval to illustrate the area under some rate function, right? And that total output represents the result based on what the scenario is or the context of the problem. But what if you knew when your interval started, but you weren't quite sure when it would end? Well, this is where an accumulator function comes into play. They become very handy. So what happens is what we know is we know when we're beginning, but we're not quite sure when it'll end. And usually you're told, well, it could be somewhere between this bound and this bound. And so it allows you to create a new function that will add up however much you need based on when you want to stop. So for example, you're starting, and this is the snow fallen example. So you might start at 3 and you don't know what the hour is. And if you said, oh, I want it to be 4 hours after midnight, you could put like a 4 here. You're like, oh no, I think I need it at 7, and then it would add up from 3 to 7. So this is a very powerful tool that allows you to add up to an unknown end if you know when you're beginning. So this is the definition of an accumulator function. So it's your function f is integrable over your closed interval, okay? So you can create, if that's true, you can create a definite integral from a to x, where x is some value that's bounded in your closed interval. See that? It's between a and b. But here's the thing to notice. Your function and your differential here now are of a different variable. They're not of x. So just use t as a placeholder. So the area is still of x because you're saying I'm going to start at a, which is the beginning of the interval, and I'm going to end it at some number that's between or in that interval. So let's see how these are actually created in practice. In this scenario here, we're going to create an accumulator function, and then I'm going to show you how it can be turned into a polynomial. So here's the scenario, or here's the problem. Let f of t equal 1 plus 2t for t in the closed interval 1 to 6. Write the accumulator function, called a of x, to represent the area under the graph of f of t over the time interval from 1 to x. Then express a of t as a polynomial in terms of x. Alright, so in order to write an accumulator function, remember it's a definite integral where you have a beginning and an unknown end. So this is going to be the interval for my accumulator function. Okay, my accumulator function. So it's going to start at 1, it's going to end at x. And it's going to be my function in terms of t dt. In this particular case, that means it's going to be the integral from 1 to x of f of t. Now what I want to do is I want to actually set up or convert this into a polynomial in terms of x. And here's how we're going to do that. At this point with our definite integrals, what we know is area. So let's use area models to come up with an expression. So what I first want to do is come up with a graph of this function 1 plus 2t. Based on this graph, now I can see it's linear. It has a y-intercept of 1, and the slope is positive 2. So I'm just going to sketch an arbitrary increasing line. Now my interval is here, 1 for sure. So it's going to definitely start at 1, but I'm not sure where it's ending. We'll look at our interval up here. The time is only going from 1 to 6. So what this tells me is my x is bounded in that interval. So add this to your accumulator function. So this x value that we're going to select is only going to be somewhere between 1 to 6. So the possible farthest this could go is 6, but it doesn't have to go to 6. Basically what we're going to do, if you can imagine, we're going to start at 1 and we're going to add up this area anywhere to the right of 1, but no more than 6. So x is whatever that value is. So what I'm going to do is I'm just going to place an arbitrary x here and just say, let's pretend that's where it is. So then this is the area we are adding up. This x value is anywhere between 1 and 6. At most 6, at the least 1. Now if you notice, this is a trapezoid. So what we're going to do now is we're going to come up with the dimensions of the height, the base 1, the base 2, and we're going to put that in the formula for the area of a trapezoid. And what we're going to end up with is a polynomial expression. And that expression could be used to approximate, or excuse me, come up with or accumulate the area under this function depending on what x is. Remember, x represents some number between 1 and 6 on this interval. So now let's start calculating our dimensions of our trapezoid. Base 1, that length is based off of the input of 1 into our f of x, or f of t function. So base 1 is equal to f of 1. So that equals 2. So remember, f is 1 plus 2t. Base 2, right here, is whatever the function is evaluated at x. Now, the height of the trapezoid is what's sitting on the x-axis, so that's this distance right here. What we're basically going to do is we're going to take this distance minus this distance, and we're left with what we want. So this big distance is x minus, what do we want to take away? 1. So then what's left over is your height. Now we have everything, so we're going to rewrite our a of x in terms of polynomials now using our information here and the area of a trapezoid formula. Now what I'm going to do here is I'm going to apply the half to the second quantity here. Now I can do that. For example, if I have 2 times 3 times 5, I could do 2 times 3 and then times that by 5. I could do 3 times 5 and then multiply by 2. I could do 2 times 5 and then multiply by 3. So you see we have 3 quantities here. So I'm going to apply the half to the second quantity here because those are all quantities that are divisible by 2. So this formula will give you the accumulation of the area under this curve on the interval from 1 until any number that you pick that is between 1 and 6. As an integral, that accumulator function looks like this. So we have our bounds, 1 to x, we have our function, we have our differential, and we have our interval for the upper bound. Don't forget to put that interval there. Now something to think about, see this trapezoid? As x gets closer to 6, that area is going to get larger, isn't it? As x gets closer to 1, the area will get smaller. So this is pretty cool because this allows you to work with a variable unknown, right? An ending point that you don't know. It's almost like in Desmos if you have a little slider there.